You feel it every moment of your life. The soft pull that keeps you grounded, the silent weight that hugs your body to Earth, the thing that keeps oceans from floating into the sky, the moon in orbit, the air you breathe gently pressing down upon you. It feels so obvious, so natural, that we barely question it. But what if I told you gravity isn't actually a force? Not in the way you were taught, not in the way your body tells you. This thing that shapes planets, drives stars to collapse into singularities, that even guides galaxies through the cosmic web, is not a force pulling on objects. Instead, it is something more elegant, more mysterious, and more profound. Gravity is geometry. It is the shape of spacetime itself. This might sound bizarre, but by the end of this journey, you will see gravity not as some invisible hand, but as the dance of matter and space, bending and weaving reality itself into patterns far stranger than fiction. So take a breath. Imagine the ground beneath you not as something holding you up, but as a curved surface gently nudging your path. This isn't just a new way to see gravity, it is a new way to understand the nature of existence. If that idea stirs even a flicker of curiosity, a simple like or subscribe helps bring more of these cosmic explorations into the world. Thank you. Now, let us begin. Before we reinvent gravity, we need to understand how it was originally conceived. In the year 1687, a man named Isaac Newton published a book called Philosophia Naturalis Principia Mathematica. In it, he proposed an idea that would dominate physics for over 2 centuries, that every mass in the universe attracts every other mass with a force. Drop a stone, and it falls to the ground. The Earth pulls it down. The moon stays in orbit because Earth pulls it in just enough to keep it from flying off. Planets dance around the sun, stars orbit within galaxies, all due to this invisible tug, this gravitational force. Newton even formulated a precise law to describe it. Two masses attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This was astonishing. Suddenly, the motion of a falling apple and the motion of the moon could be described by the same law. The heavens and the earth were unified under a single principle. But Newton's law was more than just elegant, it was powerful. It could predict the motion of planets, guide ships by the stars, and even allow astronomers to discover new celestial bodies. Neptune, for instance, was found by calculating how Uranus's orbit was being perturbed by an unseen gravitational influence. That's how confident we were in Newton's gravity. So confident, in fact, that when something didn't fit, we assumed the universe was wrong, not the theory. But before we get to the cracks in Newton's model, consider this. Gravity is extraordinarily weak. Yes, you heard that right. It might feel strong when you fall, but in the grand scheme of fundamental forces, gravity is astonishingly feeble. For example, the electromagnetic force between two electrons is roughly 10 to the power of 39 times stronger than the gravitational attraction between them. That's a 1 followed by 39 zeros. Gravity only wins on large scales because it is always attractive. Mass can't cancel mass the way charges can cancel charge. In fact, to detect a gravitational wave, a ripple in space-time itself, we need detectors that are kilometers long, shielded from every vibration, and so sensitive they can detect a change in length smaller than 1/10,000th the width of a proton. That's the scale of subtlety we're dealing with. So, while Newton's gravity was good enough to navigate the solar system, it would soon be stretched beyond its limits by a single, stubborn planet. That planet was Mercury. Unlike the other planets, Mercury's orbit showed a slight but persistent anomaly. Over time, its closest approach to the Sun, the perihelion, was shifting more than Newton's laws could account for. Astronomers tried to fix this by adding a hypothetical planet Vulcan closer to the Sunday, but Vulcan never showed up. Other corrections failed too. This anomaly wasn't huge, just a few dozen arc-seconds per century, but it was enough to whisper, something is missing. This wasn't just a fluke, it was a message, and it would take a new way of thinking, a radical leap to resolve it. That leap would come in the early 20th century, from a man named Albert Einstein. But before we go there, Ask yourself this: what does it mean for something to pull on something else? How can a mass here affect a mass way over there through empty space with no physical connection? Newton himself was uncomfortable with the idea of action at a distance. He described it as an absurdity and admitted he had no explanation for how gravity worked, only that it did. So, imagine, what if masses don't pull at all? What if instead they shape the very fabric around them, and other objects follow the curves? It's an idea so beautiful, so strange, and so precise that once you understand it, you'll never see reality the same way again. And it starts with one critical insight: space is not flat. To truly grasp Einstein's revolution, we must first reimagine what we mean by space and by time. For most of history, we treated them as separate. Space was the three-dimensional arena in which matter moves length, width, and height. Time, meanwhile, was the steady, ticking rhythm that moved forward, unaffected by what happened within space. They were distinct and absolute, but in the early 20th century, Albert Einstein shattered that separation. In his theory of special relativity, he proposed that space and time are fundamentally intertwined. Together, they form a unified four-dimensional fabric, spacetime. This wasn't just a mathematical trick, it was a profound shift in how the universe operates. In this new picture, the geometry of space is inseparable from the flow of time. And here comes the breathtaking idea. Gravity is not a force acting at a distance. It is the warping of this space-time fabric by mass and energy. Imagine placing a heavy sphere on a stretched rubber sheet. The sheet bends. If you now roll a smaller ball across the surface, it doesn't move in a straight line, it curves, following the shape of the dip. This is what Einstein proposed. Massive objects like stars and planets bend the space-time around them, and other objects move, not because they're being pulled, but because they are simply following the straightest possible path in a curved geometry. These paths are called geodesics, the natural trajectories objects follow when no other forces are acting. So, when an apple falls from a tree, it's not being yanked downward by an invisible hand. It is tracing a geodesic through curved space-time, shaped by the Earth's mass. This changes everything. Let's bring it closer to home. You are sitting or perhaps standing right now, and you feel your weight pressing down. But from the perspective of general relativity, you are not moving along a natural geodesic. The surface beneath you is applying an upward force to keep you still, resisting your urge to follow the curve of space-time. In contrast, when you jump into the air, you are briefly free. For a fraction of a second, you are in free fall. That sensation of weightlessness isn't because gravity disappeared, it's because nothing is resisting your natural motion. You are following the geodesic that space-time has laid out for your body. This leads to one of Einstein's most elegant insights, the principle of equivalence. He proposed that there is no physical difference between free fall and being at rest in deep space far from any mass. Imagine two elevators, one falling freely in Earth's gravity and another floating in the void of space. Inside, you would feel exactly the same, weightless, suspended, untethered. This equivalence is not just a poetic analogy, it is the cornerstone of general relativity. It tells us that acceleration and gravity are intimately related, that motion through space-time can bend time itself, that the force we feel is not from space acting on us, but from us resisting the flow that space-time wants us to take. Let's take this further. Consider astronauts aboard the International Space Station. They appear to float effortlessly in their spaceship. Many assume they are beyond gravity's reach, but they are not. In fact, gravity at that altitude is only slightly weaker than on Earth's surface. What's really happening is that the space station and its inhabitants are in continuous freefall. They are falling around the Earth, constantly missing it, tracing a geodesic through curved space-time. And because everything inside falls together, they experience weightlessness. No floor pushes back, no resistance halts their motion. They are passengers on a curved trajectory that space-time naturally provides. The same principle explains why satellites orbit, why planets circle the Sunday, why stars drift through the arms of galaxies. not because some invisible rope pulls them inward, but because their motion through a curved spacetime keeps them on the edge of falling. And this understanding explains Mercury's mystery. Remember that stubborn discrepancy? The precession of Mercury's orbit, how it rotated just a little too much over time? Einstein's new model predicted it exactly. When you account for the curvature of spacetime near the massive Sun, Mercury's geodesic path shifts ever so slightly, not in a chaotic way, but in a precisely calculable arc. A prediction that Newton's gravity failed to match, but Einstein's spacetime curvature described perfectly. It was the first major confirmation of general relativity. But how do you test such a radical idea? Einstein proposed an extraordinary prediction. If mass bends spacetime, then light itself should be affected, not because light has mass, but because it travels through this curved geometry. During a total solar eclipse in the year 1919, astronomers pointed their telescopes towards stars near the sun's edge. According to Newton, light should not be bent, but Einstein said the stars would appear slightly displaced because their light would curve as it passed near the sun's massive body. And they were. The measurements matched Einstein's predictions. The stars danced around the sun's edge, not because they had moved, but because the path of their light was bent by warped spacetime. The front pages of newspapers declared, Einstein's theory triumphs. But this was just the beginning. Once we accept that spacetime bends and curves in the presence of mass and energy, a new vision of the cosmos unfolds. Time itself flows differently depending on gravity's pull. Clocks tick more slowly near massive bodies. GPS satellites, orbiting above Earth, must correct for time dilation to maintain accuracy using both special and general relativity. Light shifts its color as it climbs out of gravity wells. Beams stretch, lose energy, shift toward red, an effect known as gravitational redshift. Even the geometry of space around rotating objects becomes twisted, a phenomenon called frame dragging. The Earth's spin gently drags spacetime around it, like honey stirred with a spoon. These are not abstract ideas. They are measured, tested, and used every day. And yet, they hint at something deeper. That gravity is not just a thing that acts, it is the shape of reality itself. That space and time are not passive backgrounds, but dynamic participants in the cosmic play. It is a strange, beautiful picture, but even this picture will soon begin to crack. In part 3, we'll enter the domain where curvature grows extreme, where the geometry of space-time tears itself into oblivion, where light cannot escape, where time seems to stop, where gravity, finally, becomes truly terrifying. We are heading into the black hole. When spacetime bends gently, we get orbits, tides, weightlessness, and clocks that tick slightly differently. But what happens when the bending becomes severe? When mass compresses itself into such a tight space that even light, the fastest thing in existence, can no longer escape? We step into the realm of black holes. These are not just dense objects. They are ruptures in the fabric of reality, places where our current understanding of physics stretches beyond its breaking point. They do not pull things in like vacuums. Instead, they curve spacetime so deeply that all possible paths, even those of photons, inevitably lead inward. Let us trace how they come to be. Imagine a star much more massive than our Sunday. For most of its life, it maintains a delicate balance. Gravity pulls inward, while nuclear fusion pushes outward. This balance keeps the star alive, burning hydrogen into helium, and later, heavier elements. But eventually, fuel runs out. When that happens, there is nothing to resist the crush of gravity. The core collapses. If the mass is sufficient, the collapse continues not just to a denser state, but to a singularity, a point of infinite density where the known laws of physics cease to apply. Surrounding this point is the event horizon, the boundary beyond which no information can escape. It is not a physical surface. You would not feel it passing beneath your feet. But once crossed, there is no way back. Even if you were a beam of light aimed perfectly outward, you would fall inward forever. This invisible surface defines the point of no return. For a non-rotating black hole, this boundary occurs at a specific radius called the Schwarzschild radius. named after the German physicist who first derived the solution to Einstein's equations that described a static black hole. For a black hole with the mass of the Earth, this radius would be less than 2 centimeters. Compress our entire planet to that size, and it would become a black hole. Let that sink in. But the terror and fascination of black holes doesn't end at the horizon. Venture close, and strange effects begin to unfold. One of them is spaghettification, a real scientific term. If you fell feet first into a stellar mass black hole, the gravitational difference between your head and your toes would be so extreme that you would be stretched into a long, thin filament, not crushed, stretched. This happens because gravity is not uniform. The closer you get, the more it changes across even small distances. This stretching force is called a tidal force, and near black holes, it grows unimaginably strong. For smaller black holes, you would be torn apart well before crossing the event horizon. But for larger ones, say, supermassive black holes lurking at the center of galaxies, the tidal forces at the event horizon might be gentle. You could cross the horizon without noticing anything unusual until it was far too late. From the outside, however, your fall would look very different. To a distant observer, you would appear to slow down as you approach the event horizon. Your signals would become increasingly redshifted, fainter, stretched in time. You would seem to freeze just above the edge, suspended forever in gravitational time dilation. But from your perspective, you would fall in, normally time would flow as usual. This contradiction is not a flaw. It is a consequence of how spacetime warps time itself. Black holes challenge more than our senses. They challenge the very foundations of physics. Because at the center, if center even makes sense anymore, lies the singularity. A point where curvature becomes infinite. A place where the equations break, where our tools become useless. And yet, the singularity is protected by the horizon. Whatever happens within cannot affect the universe beyond. This is known as cosmic censorship, the idea that nature hides its deepest chaos behind a veil. But what if it doesn't? There are hypothetical solutions called naked singularities where no horizon exists. These are theoretical oddities, but if real, they would expose the raw singularity to the universe, tearing open causality and predictability. Time itself might fracture, and so the black hole becomes not just an object, but a philosophical question. Is reality fundamentally knowable? Is there a boundary to comprehension? Einstein never believed black holes were real. To him, they were mathematical artifacts. But over time, evidence mounted. We have watched stars orbit something invisible and incredibly massive at the heart of our galaxy, Sagittarius A*. We've seen the light of background stars warped by their presence. We've heard the tremble of space itself as black holes collide. And in two monumental moments, first in 2019 and again in 2022, we photographed the shadows they cast. Using a planet-sized telescope array called the Event Horizon Telescope, scientists captured the silhouette of a black hole against the glowing plasma around it. Not the black hole itself, but the absence of light, the echo of where space-time collapses inward. It was not just a scientific triumph. It was a moment of awe, a way to see the invisible. Yet, the story doesn't end there. In fact, it gets even stranger, because black holes are not entirely black. In 1974, Stephen Hawking proposed that black holes are not eternal. Due to quantum effects near the event horizon, they slowly emit radiation now known as Hawking radiation. Over vast timescales, black holes can evaporate. But this leads to a terrifying paradox. If a black hole evaporates completely, where does the information go? Does it vanish? That would violate one of quantum mechanics' most sacred rules. That information is never lost. This is the black hole information paradox, and it remains one of the deepest unsolved problems in physics. Does information somehow escape? Is it encoded on the event horizon, as in the holographic principle? Is space-time itself a projection of something more fundamental? We do not yet know. But in this paradox lies a crossroads, a place where quantum mechanics and general relativity collide. Neither is willing to yield. And so, we are forced to look deeper, to search for a unified theory, a theory of everything. For now, black holes remain the guardians of secrets. They are cosmic doors that swing only one way. They hold within them not just mass, but mystery, not just gravity, but the tension between what we know and what we still cannot grasp. In the next part of our journey, we'll listen to the ripples they send across the universe. Because when black holes collide, the fabric of spacetime itself sings. Gravity, we've said, is not a force, it's the geometry of spacetime itself. And if that's true, then when something massive moves suddenly, it should send ripples through that geometry, just like a stone dropped into still water. These ripples are known as gravitational waves. They are distortions in spacetime that travel at the speed of light, stretching and compressing the fabric of reality as they pass. They are not sound. They are not light. They are not particles. They are pure motion of the very thing that underlies existence. And for 100 years, they were only theoretical. Albert Einstein first predicted them in 1916, shortly after formulating his general theory of relativity. But even he doubted we'd ever detect them. They were too subtle, too faint, like trying to hear the flutter of a butterfly's wing during a thunderstorm. But space-time does tremble. And now we can hear it. To understand gravitational waves, imagine two massive objects orbiting one another like two black holes or two neutron stars. As they spiral inward, they disturb space-time, sending waves outward in all directions. These waves carry energy. They take it away from the orbiting pair, causing them to draw closer, spin faster, and eventually merge in a violent crescendo. When the waves finally reach us, after traveling for billions of years, they stretch and squeeze space itself. The distances between objects on Earth change ever so slightly, not enough for your eyes to notice, not enough for buildings to shift, but just enough for the right instruments to detect. And that instrument is called LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory. It consists of two enormous detectors in the United States, each shaped like an L with arms 4 kilometers long. A laser beam is split and sent down each arm, bounced back by mirrors and recombined. If a gravitational wave passes through, it will subtly change the lengths of the arms, causing the recombined light to shift in a detectable way. But here's the scale we're talking about. LIGO is designed to detect changes in length smaller than 1/10,000th the diameter of a proton. That's like measuring the distance to the nearest star over 4 light years away to within the width of a human hair. It is one of the most sensitive instruments ever built. And in September of 2015, it worked. Two black holes, one about 29 times the mass of the Sun, the other about 36, had been spiraling toward one another for millions of years. In the final moments of their merger, they sent out a gravitational wave so powerful that, for a brief instant, it released more energy than all the stars in the observable universe combined. That wave traveled across space for over 1 billion years. It passed through galaxies, nebulae, and voids, untouched. Then it reached Earth, and LIGO heard it. A chirp. That's how scientists describe the signal. A tiny rise in frequency and amplitude that matched exactly what Einstein's equations predicted. For the first time, we had not just seen the universe, we had heard it. That moment changed everything. It confirmed that gravitational waves were real. It validated a century-old prediction. But more than that, it opened a new way of observing the cosmos. Until then, astronomy was based entirely on light. Telescopes captured visible light, infrared, X-rays, gamma rays. But light can be blocked, scattered, or absorbed. It can be deceptive. Gravitational waves, by contrast, pass through everything. They carry information from places light cannot escape, like the hearts of black hole collisions. We had gained a new sense, a way to feel the universe's deep events. This is the beginning of multi-messenger astronomy, combining light and gravity to tell the full story of the cosmos. LIGO was soon joined by another detector, Virgo, in Italy. With multiple observatories, scientists can triangulate the origin of waves in the sky, like using two ears to locate a sound. Then came Kagra in Japan, and more are planned. A global network, listening to the whispers of spacetime. Each new detection adds to the cosmic symphony. Black holes merging, neutron stars colliding, strange remnants echoing through the void. In 2017, a gravitational wave was detected from two neutron stars colliding. This time, light was also observed: gamma rays, visible light, X-rays. Telescopes around the world pointed at the explosion. We saw a kilonova, an event so powerful it forges elements like gold and platinum. Yes, the gold in your ring may have been born in a collision that rippled space-time a billion years ago. Think about that. Gravitational waves do more than confirm our theories. They teach us what we didn't expect. They hint at primordial waves fossils from the Big Bang itself. If detected, they could reveal the conditions of the infant universe, mere moments after time began. They raise new questions. What happens inside the event horizon after a merger? Could there be exotic, compact objects, not black holes or neutron stars, but something stranger? Could gravitational waves one day test theories of quantum gravity, string theory, or even alternate dimensions? We don't yet know, but every ripple brings us closer. There's something poetic about all this. The universe has been ringing for billions of years. Stars explode, galaxies collide, black holes embrace, and space itself vibrates with their passing. Until recently, we could not hear it. We saw light and shadow, but not the trembling beneath. Now, at last, we do. Instruments like LIGO and Virgo do not just measure, they listen. They transform space-time's invisible pulse into something we can study, interpret, even feel. It's not loud, it's not dramatic, it's subtle, a cosmic whisper crossing the abyss. And we small, soft, mortal creatures have built the ears to hear it. Gravity is subtle, it is gentle, but given enough time, it becomes the master architect of everything. It built the planets, gathered the stars, and stitched together galaxies. It bound atoms of hydrogen into luminous spheres and spun vast clouds of gas into spiral arms. But the true artistry of gravity lies in what we cannot see. For most of cosmic history, we have looked up and seen only part of the picture. Light, as beautiful as it is, shows us just a sliver of the whole. Stars, nebulae, glowing filaments, all these are merely the lanterns. But what holds the lanterns? What we discovered is this: most of the universe does not shine. In fact, most of the universe is dark. It began with a simple observation. When astronomers measured how stars moved within galaxies, they expected to see something predictable. Stars closer to the center should orbit faster, while those farther out should move more slowly, like planets in our solar system. But that's not what they found. Instead, stars far from the galactic center were orbiting just as fast as those near the core. The outer stars were moving too quickly to be held in place by the visible matter alone. Something invisible was exerting extra gravitational pull, something that did not emit or absorb light, something massive, yet hidden. This unseen mass was dubbed dark matter, and its fingerprints were everywhere. Dark matter holds galaxies together. Without it, spiral galaxies would fly apart. It surrounds them in vast halos, reaching far beyond the glow of stars. It binds galaxies into clusters and connects clusters into sprawling filaments, a cosmic web stretching across the observable universe. It can even bend light. When light from a distant galaxy passes near a massive cluster, the gravity of that cluster warps spacetime, distorting the path of the light. This effect is called gravitational lensing, and it allows astronomers to see dark matter indirectly by watching how it bends what lies behind it. Through lensing, we can map the invisible, and what we see is astonishing. The luminous matter, the stars and galaxies we photograph, is just a faint frost clinging to enormous scaffolding. The real structure of the universe is made of something we do not yet understand. According to current estimates, dark matter makes up roughly 27% of the universe. All the stars, planets, gas, and galaxies combined, less than 5%. The rest is even stranger. In the late 1990s, Two teams of astronomers were measuring the expansion rate of the universe. Ever since the Big Bang, space itself has been stretching. The assumption was that this expansion would gradually slow over time due to gravity. But the data revealed the opposite. The expansion was not slowing down, it was speeding up. This was completely unexpected. Some unknown energy was pushing the fabric of space apart, accelerating the growth of the universe. And like dark matter, it could not be seen. It had no glow, no signal, no interaction with light. It was named dark energy. And if the numbers are right, dark energy accounts for about 68% of everything. We do not know what dark energy is. We only know what it does. It fights gravity. It stretches the universe ever faster. It dominates the cosmic ledger. This means that 95% of the universe is invisible and unexplained. The stars are not the story. They are the punctuation marks. The story is written in shadow, but gravity, paradoxically, helps us reveal the darkness. Because it obeys no veil, it responds to mass and energy seen or unseen. Wherever there is curvature, gravity speaks. It pulls, it shapes, it tells us that something is there. In that sense, gravity is our most honest guide. It led us to the galaxies, then to the halo of dark matter around them, then to the filaments that thread them together, then to the accelerated expansion driven by dark energy. And perhaps one day, it will lead us further still to new particles, new fields, new understandings of the void. The universe is not evenly filled. It has texture. Vast voids span hundreds of millions of light years, nearly empty. Between them are walls and filaments, where galaxies cluster like dew on a cosmic spiderweb. These structures were not pre-designed. They emerged from tiny fluctuations in the early universe, amplified by gravity over billions of years. Imagine, the same gravity that holds you to your chair also sculpts the universe on scales so large, light takes eons to cross them. From the flicker of a candle to the motion of superclusters, gravity governs it all. It does not ask to be noticed. It only shapes, and yet gravity may also shape the fate of everything. If dark energy remains constant, the universe will continue expanding faster and faster. Galaxies will drift beyond our view. Stars will burn out. Black holes will evaporate. Even atoms may decay. This future is known as the heat death, a cold, dark, and lonely cosmos, stretched thin by eternity. But if dark energy changes, if it strengthens or weakens, the fate shifts. The universe could rip apart, shredding even the atoms in your body. Or it could slow, stop, and collapse back inward in a big crunch, perhaps leading to another rebirth. Or something we haven't imagined could occur because we are still infants, staring at shadows on the wall of a cave. Gravity is the thread that connects everything. It binds the atoms in your bones and the galaxies in the sky. It whispers through space-time and sculpts the skeleton of the cosmos. It is ancient, tireless, and endlessly subtle, but perhaps its most remarkable gift is this. It makes the universe knowable, because gravity is predictable, measurable, testable, even when what it points to remains invisible. Even when what it reveals is wrapped in darkness, gravity doesn't just hold the universe together. It helps us understand it. Time feels universal, a constant beat beneath our lives. 1 second here, 1 second there, surely the same everywhere, for everyone. But gravity disagrees. In Einstein's universe, time is not an independent rhythm ticking in the background. It is not a cosmic metronome. Time is woven together with space. Both are aspects of a single, flexible fabric. And just as gravity curves space, it also curves time. It slows it down. It stretches it. It makes time flow differently depending on where you are and how fast you're moving. This isn't poetry. It's physics. And it's measurable. Right now, as you sit or stand reading these words, time is flowing just a little slower for your feet than for your head. This effect is called gravitational time dilation. The closer you are to a massive object, the more spacetime curves. And in that curvature, time stretches. Clocks run slower, not because the clock is broken, but because time itself is passing more slowly. This was once just a prediction. Now it's tested, confirmed, and corrected for every day. In the 1970s, physicists flew atomic clocks aboard airplanes and compared them to identical clocks left on the ground. The airborne clocks ran slightly faster, just as Einstein predicted. They were higher up, farther from Earth's gravitational pull, and so time passed differently for them. And the difference wasn't negligible. In fact, without constant corrections for both general and special relativity, your phone's GPS system would drift by kilometers every single day. Yes, gravity affects your ability to find coffee, but let's go deeper. Imagine standing near the surface of a massive planet. Your twin remains far above, floating freely in orbit. You each carry an identical clock. After a few years apart, you reunite and compare clocks. Yours ticks behind. You have aged more slowly. This isn't a sci-fi twist. It's a truth of nature. In fact, if you lived your life on the surface of a neutron star, a city-sized sphere of ultra-compressed matter left behind by a supernova, you would age much more slowly than someone on Earth. A minute for you might be hours elsewhere. Time, it turns out, is elastic, and gravity stretches it. The most famous portrayal of this concept may come from the film Interstellar. In one scene, astronauts land on a planet near a supermassive black hole. The gravitational pull is immense. They spend just over an hour on the surface, but when they return to their ship, orbiting farther out, they find that 23 years have passed. The scene is heartbreaking. One man waited, alone, for decades. Another lost time with his daughter that he could never reclaim. And yet, the physics behind that scene is real. The effect is extreme, but mathematically sound. Near a black hole, time slows down dramatically. For someone at a safe distance, your descent toward the event horizon appears to take forever. But for you, it feels immediate. Time is not absolute, it is relative. It bends with gravity, and this has a profound implication. Now is not universal. We often imagine time as a sequence of nows stacked across the universe. Right now on Earth, right now on Mars, right now in another galaxy. But in relativity, that concept falls apart because time flows differently for different observers in different gravitational fields. There is no single now that applies everywhere. Your present might not match someone else's. Their clocks run at different speeds. Their timelines diverge. This isn't just theoretical. Even on Earth, high-precision clocks placed just 30 centimeters apart, say, one on a table, one on the floor, tick at slightly different rates. Gravity is that precise. Time is that delicate. Our experience of now is local. It is shaped by where we are and how space-time curves around us. This realization forces a question. What is time, really? We often treat it as a flowing river, but in physics, time is a dimension, just like left and right, up and down, forward and back. You do not move through time like a boat. You exist within time the way a point exists within space. And if time is curved, it's because gravity is changing the shape of the universe's stage. You are not just in the universe. You are in space-time, and your life, your memories, your perception of moments are all unfolding on a path through that space-time, shaped by gravity. You are tracing a geodesic not only through space, but through time. Even light, which always travels at the same speed through vacuum, experiences this curvature. When it climbs out of a gravitational well, it loses energy not by slowing down, but by stretching its wavelength. This is called gravitational redshift. Light becomes redder, lower in energy, because time at the emission point is moving more slowly than where it's being observed. Einstein predicted this too, and we've seen it. Clocks on satellites orbiting Earth tick faster than those on the surface, and the signals they send must be adjusted for both their speed and their altitude. If we ignored these relativistic effects, navigation would break down almost instantly. Again, this is not abstract. You live in curved time. Let's go even farther. Consider the early universe, a place where gravity was fierce, densities were immense, and time may have flowed very differently. Or think about black holes, where time dilates towards zero. From our vantage point, anything falling into a black hole seems to slow and freeze, asymptotically approaching the event horizon, never quite crossing. But from the falling object's own frame, time proceeds normally. They cross the horizon in a finite moment. So whose time is real? Both and neither. Relativity tells us that time is not a thing you can hold. It's not something that exists independently of the observer. It is shaped by gravity, and it shapes your experience of the universe. Time is personal, and gravity is the sculptor. As we move through life, we feel time as a flow. Seconds tick, days pass, years accumulate, but deep down, what we feel may be something more mysterious. The way our consciousness tracks its motion along a curved path through spacetime. Maybe memory is not about events fading into the past. Maybe memory is how we experience curvature. Maybe time is not a river, but a landscape, and you are walking it, moment by moment, shaped by gravity's invisible hand. We've spoken of gravity as sculptor, of time as curved, of black holes as boundaries in space-time. But now, we stand at the ultimate edge. Not the edge of a black hole, but the beginning of everything. The origin of gravity itself, of time, of space, of the universe. According to our best models, the universe began not with a spark, but with a sudden expansion, a violent, almost incomprehensible event known as the Big Bang. It was not an explosion in space. It was an explosion of space. There was no empty void waiting to be filled. There was no outside. All of space, all of time, all of matter and energy erupted from a single origin. A singularity, not a place, but a condition. An instant of infinite density, infinite curvature, where the very fabric of space-time began. We often picture the Big Bang as a bright point in the darkness. But there was no darkness. Darkness requires space, and space had not yet been born. So what was there before? The truth is, the question may not even make sense, because before is a word that implies time, and time itself emerged with the Big Bang. Asking what came before is like asking what's north of the North Pole. The concept dissolves. Time began when the universe began. In the earliest fractions of a second, less than 1/1,000,000th of 1/1,000,000th of 1/1,000,000th of a second, the universe underwent an incredible transformation called cosmic inflation, a burst of expansion so rapid, so immense, that the observable universe was stretched from subatomic size to macroscopic scale almost instantly. Why? We're not sure, but this inflation explains much about the universe we see today. Why it looks the same in all directions, why it is so flat, why it formed galaxies and stars, instead of remaining a smooth soup of energy. Tiny quantum fluctuations, imperfections in the early vacuum were stretched out across the cosmos during this inflation, becoming the seeds of galaxies. What was once randomness became structure, and gravity began to work. As the universe cooled, matter and energy differentiated. First, the fundamental forces gravity, electromagnetism, the strong and weak nuclear forces split from a unified field. Then particles emerged, quarks, electrons, photons, protons and neutrons formed. After a few minutes, these particles fused into the lightest elements, hydrogen, helium, traces of lithium. The universe was still opaque, a dense, glowing fog of charged particles and light, scattering endlessly, unable to travel freely. But about 380,000 years after the Big Bang, something happened. Atoms formed, electrons bound to nuclei. Light was finally free to move. This moment is called recombination, and the light released then is still with us, stretched by the expansion of space into microwaves. It is called the cosmic microwave background, and it is the oldest light we can ever see. When we look at that faint glow, we are seeing a baby picture of the universe, an image of what it looked like when it was just beginning to take shape. The temperature variations, only a few parts in 100,000, reveal the earliest imprints of gravity's influence. These tiny differences told gravity where to go, where to pull, where to gather. Over billions of years, those slight variations were magnified. Gas collapsed, Stars ignited, galaxies spun, cosmic filaments formed, superclusters gathered, voids expanded, all from ripples frozen into the microwave background. Gravity took randomness and made a cosmos. But let's return to those earliest instants, because here, once again, our understanding fails us. As we approach the singularity, our equations break. General relativity describes the large, quantum mechanics describes the small, but at the beginning at the Planck scale, just 10 to the negative 43 seconds after the Big Bang, neither theory alone can explain what was happening. We need a quantum theory of gravity, a unification, and we don't have it yet. There are hints, ideas. String theory proposes that all particles are tiny vibrating strings, and that gravity is just one of many vibrational modes. It requires extra dimensions, space beyond the familiar three. Perhaps these dimensions are curled up, invisible. Perhaps gravity leaks into them, explaining why it feels so weak. Loop quantum gravity. Another approach attempts to quantize space and time itself, suggesting that space-time is made of discrete, finite loops, that there is no smooth continuum, only quantum grains stitched together. Some theories even suggest that the Big Bang was not the beginning but a bounce, that a previous universe collapsed, reversed, and gave rise to ours. Others imagine the universe emerging from quantum fluctuation, a random event in a timeless void. But these are speculations, elegant, tempting, not yet confirmed. What we do know is this: gravity was born in the beginning. It emerged from the unified forces. It was the first to separate, the first to shape, and it has been guiding the evolution of the universe ever since, pulling matter into structure, slowing expansion where it can, yielding only to the strange pressure of dark energy. Without gravity, there would be no stars, no planets, no life, no time, as we know it. Perhaps most profoundly, gravity makes memory possible, because without gravity, matter would not clump, no complex systems would form, there would be no brains, no storage of information, no observers, and without observers, time itself has no meaning. It is gravity that creates the arrow. It is gravity that allows change, decay, growth, and reflection. It is gravity that gives us a history, a sense of past, present, and future. So, when you look up at the night sky, you are not just seeing stars, you are seeing the aftermath of a beginning so strange that our best minds still struggle to describe it. You are seeing the result of gravity acting on the very first ripples of existence. And you are a part of that story, a ripple made flesh, a pattern shaped by the same forces that sculpted galaxies. You are the universe, remembering itself. We began at the start, the birth of space, the awakening of time, the sudden release of gravity into a newborn cosmos. But now, we look ahead, toward the distant future, a future so far removed from us that stars themselves are young by comparison, a future where gravity, still patient and tireless, continues to shape the fate of all things. This is not the apocalypse of fire or flood. It is something quieter, more final. It is the heat death of the universe. In the beginning, the universe was hot, dense, and bright. Stars formed rapidly, galaxies bloomed, black holes grew. Now, over 13 billion years later, things are slower, cooler, more diffuse. And it will only continue. Stars will burn out, not all at once, but gradually, one by one. The massive ones will go first, living fast, dying in supernova explosions that scatter elements across space. Their cores may collapse into neutron stars or black holes. Smaller stars, like our Sun, will last longer, gently shedding their outer layers to become white dwarfs. These stellar embers will glow for trillions of years, then fade into darkness. The universe will dim, and eventually, there will be no new stars. But gravity is not finished. Even as stars die, gravity continues its work. It pulls rogue planets into quiet orbits around cold remnants. It shepherds matter into dense clumps. And over unimaginable spans of time, galaxies themselves may dissolve, Through a process called dynamical relaxation, stars in a galaxy exchange energy through gravitational encounters. Some are flung into intergalactic space, others fall inward, feeding central black holes. Given enough time, galaxies will thin and vanish. The night sky will go dark. Then begins the black hole era. In this epoch, black holes will be the last luminous objects in the universe, not because they shine, but because they move, merge, and sometimes collide. Each collision sends out gravitational waves, whispers in the void, echoes of ancient mass meeting ancient mass. Eventually, even black holes will grow quiet, except for one final trick. They will evaporate. This idea, first proposed by Stephen Hawking in the 1970s, says that black holes are not entirely black. Quantum fluctuations near the event horizon allow for the creation of particle-antiparticle pairs. One falls in, the other escapes. The black hole loses energy, shrinks, and over unimaginable timescales, 10 to the 100th power years, or more, it will vanish. This is called Hawking radiation. Tiny black holes go first. The supermassive ones, the giants at galactic cores, will be the last. But eventually, all will fade. Not in a bang, but in a slow hiss of quantum breath. Nothing will remain but low-energy radiation, drifting across a cold, stretched cosmos. This is the degenerate era. No stars, no light, only remnants. Planets without suns. White dwarfs cooled to black. Neutron stars inert. Space dust frozen in time. Black holes fading. Gravity, at last, begins to lose its grip. But even then, something else continues. Decay. Some theories suggest that protons, the building blocks of matter, are unstable. If that's true, over 10 to the 34th power years, they will decay. Hydrogen, the most abundant element, will dissolve. Atoms themselves will disappear. If protons do not decay, matter may persist in frozen silence. But if they do, only energy will remain. A thin mist of particles. No stars, no structures, no gravity as we knew it. And then, the dark era, a universe without complexity, without heat gradients, without memory. Entropy reaches its maximum. No engines run, no reactions occur, no observers watch. Space expands into colder and colder emptiness, its fabric stretched so thin that all interactions cease. Photons lose energy. Time loses meaning. Nothing happens because nothing can. This is the end of time, not because clocks stop ticking, but because there is no longer any difference between one moment and the next. A frozen stillness, perfect symmetry, perfect silence. This might sound bleak, but perhaps it is not a tragedy. Perhaps it is completion. A vast story written in hydrogen and helium, told through stars and gravity, and ending in stillness. A return to calm. And in that final hush, there is a kind of beauty, because what preceded it was not empty. It was full of galaxies and dreams, of eyes that looked up and asked questions, of beings who traced the shape of time with wonder. The silence means the song was sung. Still, physicists wonder, is this truly the end? Some theories suggest not. Maybe dark energy is not constant. Maybe it will reverse, and gravity will triumph again, pulling everything inward in a big crunch, a cosmic implosion that ends in fire, not frost. Or perhaps the universe is part of a cycle expansion, collapse, rebirth, an eternal loop. There are even theories of the Big Rip, where dark energy grows stronger, pulling galaxies apart, then stars, then atoms, until space-time itself unravels. And others speculate on baby universes budding off from black holes, new realities born in silence, unreachable from ours. The truth is, we do not know. Our vision grows dim in the far future. The math continues. The predictions stretch forward, but certainty fades. And in that uncertainty lives wonder. Even now, gravity continues its quiet work. It binds our world, shapes our lives, draws oceans into tides, bends light from distant stars, holds galaxies in their orbits. And yet, one day, it too will yield. Not because it disappears, but because there will be nothing left to shape. No masses to move, no structures to maintain, no curvature to measure, just the memory of motion, stretched across time. But here is the miracle. You are here. For a brief flash, in this vast arc of silence and fire, you exist. You are a self-aware ripple in the fabric of space-time, a collection of atoms shaped by gravity, born in stars, now contemplating the fate of the cosmos. You are a witness, and that may be the rarest thing the universe has ever made. We have followed gravity across time, from the instant of creation to the final silence. We have watched it sculpt stars, stretch space, slow time, and whisper through black holes. But gravity has a secret, a contradiction, and that contradiction lies at the heart of everything we do not yet understand. Because, while gravity explains the galaxies, the motion of planets, the curvature of space it breaks down when we dive into the very small, and quantum mechanics, which governs the small, refuses to play by gravity's rules. These two great theories, general relativity and quantum mechanics, are both breathtakingly successful. They have passed every test, explained every observation in their realms, and yet they do not agree. The tension becomes clearest inside a black hole. As we've seen, Einstein's gravity tells us that a black hole is defined by its event horizon, a boundary beyond which nothing, not even light, can escape. At its core lies the singularity, a point where density becomes infinite and space-time curvature becomes undefined. But quantum mechanics resists this idea, because at small scales, nothing is truly continuous. Space, time, energy, they all come in discrete packets. Quanta, the smooth fabric of space-time, begins to fray. At the Planck scale, about 10 to the negative 35 meters, quantum fluctuations are no longer negligible. Space-time is thought to become a chaotic, foaming mess of energy, a seething sea where geometry itself flickers. Here, general relativity fails. Its equations demand continuity, but the quantum world denies it. Nowhere is this conflict more dramatic than in the black hole information paradox. It begins with Hawking's idea that black holes emit radiation, that over time they evaporate, shrinking until they vanish completely. But here's the problem. Hawking's radiation appears to be random. It does not seem to carry any information about the matter that fell into the black hole. This would mean that when the black hole disappears, information is destroyed. And in quantum mechanics, that is forbidden. Information about particles, their states, their interactions, must always be preserved. It may become scrambled, hidden, entangled, but it cannot be lost. If it is, quantum mechanics falls apart. But if information is preserved, how? Where does it go? Does it escape? Linger on the horizon? Or remain encoded in the radiation somehow? There is no consensus, only paradox. Some physicists suggest that information is stored on the event horizon itself, that the horizon acts like a kind of hologram, encoding all the information about what's inside on its two-dimensional surface. This idea, known as the holographic principle, is one of the most radical in modern physics. It proposes that our three-dimensional universe may actually be a projection of information encoded on a distant boundary, like a hologram projecting depth from a flat surface. In this view, gravity, space, and even time emerge from deeper, more fundamental processes, perhaps quantum entanglement, perhaps something else. Our universe may not be fundamentally geometric. It may be informational. Others turn to string theory for answers. In this model, all particles are not points, but tiny vibrating strings. The different ways these strings vibrate determine the properties of particles, mass, charge, spin. Gravity arises naturally in string theory as a mode of vibration called the graviton, a hypothetical quantum particle that carries the force of gravity. But for the math to work, string theory requires extra dimensions, usually 10 or 11 in total. These extra dimensions might be compactified, curled up so tightly we cannot detect them, or vast and hidden. The theory is elegant, powerful, but it remains unproven. No graviton has ever been detected. and no experiment has yet confirmed the presence of extra dimensions. Then there is loop quantum gravity, a rival to string theory. Instead of adding dimensions, it seeks to quantize spacetime itself, suggesting that space is made of tiny loops of finite area and volume. That geometry is granular, and that time may also come in quanta individual ticks rather than a smooth flow. If correct, this would mean that space and time emerge from something even more basic, a quantum network of connections. These are bold ideas, each promising, each incomplete. At the center of these debates is gravity itself. It refuses to yield. It refuses to be quantized easily. In every attempt to build a theory of quantum gravity, gravity resists. Its behavior at high energy, its infinite singularities, its nonlinear complexity, all of it makes unification difficult. And yet, we cannot turn away, because without unification, we cannot explain the birth of the universe. We cannot resolve the paradoxes of black holes. We cannot understand what space and time truly are. We are like cartographers standing at the edge of a continent, holding two perfect maps, one for mountains, one for rivers, but unable to overlay them onto the same land. We are missing the bridge, and so physics today lives with tension. Our most successful theories point in different directions. Gravity bends space-time. Quantum mechanics collapses wave functions. Gravity is deterministic. Quantum theory is probabilistic. Gravity demands curvature. Quantum physics demands uncertainty. Each describes a different part of reality perfectly, but together they clash. And in that clash lies something beautiful, because it tells us there is more, that beneath even our best understanding, mystery endures. The paradoxes are not failures, they are invitations. They show us the cracks in the wall, places where light leaks in from the deeper structure beneath. And for the first time in history, we have the tools to explore them. Particle accelerators, supercomputers, space telescopes, gravitational wave observatories. The very fact that we can ask these questions, what is time? Where does information go? Is the universe a hologram? Is already a triumph of gravity's gift to us. Because gravity not only shaped the stars, it shaped us. It gave rise to structure, to memory, to thought, to paradox. Close your eyes, take a slow breath. Right now, wherever you are, you can feel it. Not just hear it or think about it, but feel gravity pulling you gently downward, anchoring you to the world. It presses your body into the ground, draws your breath downward in your lungs, guides your blood toward your feet. Every moment, it holds you in place, not harshly, but constantly. It is always there, always has been. Before you learned the word for it, before you understood or questioned it, you knew gravity in your bones. We often treat gravity as an external thing, something out there, governing the stars and planets, orbiting moons, and falling apples. But gravity is not just cosmic, it is intimate. It is one of the first forces your body ever encountered. In the womb, you floated, but the moment you were born, gravity claimed you. It taught you what up and down meant. It shaped your balance, your posture, your stride. It helped you fall asleep in someone's arms, and later, you felt its tug in other ways, running down a hill, leaping into water, falling in love. Yes, even metaphorically, we speak of gravity as the pull of something meaningful, something unavoidable, something real. Stand still, and gravity holds you softly. Jump, and you rise for a moment, but always return. Every muscle you move is working with or against gravity. Every breath is shaped by the atmosphere that gravity holds around you. Without gravity, there would be no oceans, no tides, no stable climate, no trees to stand tall, no rain to fall. Even your sense of weight is not about gravity alone, it is about resistance. The floor pushing back against your natural desire to follow the curve of space-time downward. You are always falling. Standing still is an illusion. Einstein showed us that gravity is not a force, but a path. Your body wants to follow the geodesic, the straightest path through curved space-time, but the ground interrupts you. It pushes back. That push is what you feel as weight. So when you are floating in orbit, you are not escaping gravity. You are surrendering to it. You are finally following the natural path your body wants to take. That is why astronauts feel weightless, not because there is no gravity, but because nothing is resisting them. They are in freefall, forever missing the planet beneath. You feel heavy not because Earth pulls you down, but because the ground won't let you go. Now imagine a world without gravity. No up, no down, no sky above, no ground below, no falling rain, no rising sun, no birth of stars, no collapse into black holes, just drifting particles in silence, no orbits, no pressure, no time as we know it. There would be no breath, no heartbeat, no memory, no meaning. Gravity does more than move matter. It creates direction. Without gravity, time has no arrow. Entropy has no gradient. There is no difference between one moment and the next. But because of gravity, things change. Things fall. Things evolve. You are not only held by gravity, you are shaped by it, both physically and temporally. You age, you grow, you decay, you remember, all because the world has a slope, a direction, a flow. Gravity gives time a slope to run down. Even your dreams obey gravity. You've likely felt it in your sleep, those moments when you stumble in a dream or fall and your whole body jerks awake. That is gravity, imprinted in your neural code, a phantom sensation wired deep in your being. Evolution has etched it into every muscle, every reflex, because for life to exist here, for creatures to walk upright, for blood to pump, for lungs to expand, gravity had to become part of the blueprint. It is not just physics, it is biology. It is story. Look at the moon. Its face always turned toward us. Its orbit, a quiet testament to gravitational resonance. Its tides pulling at our oceans and at our cells. Look at the oceans. They rise and fall like breath, like the lungs of the planet, moved by the gravitational dance between Earth, Moon, and Sunday. Look at yourself, a structure of atoms forged in stars, held together by electromagnetism, standing tall against the constant pull of gravity. You are a momentary rebellion against collapse. But gravity is not your enemy, it is your condition. There is an elegance in this. You are held to a planet that is falling through space, around a star that is falling through a galaxy, that is falling through a filament that is curved by the mass of invisible things. You are never standing still, not even for a moment. Your life is a trajectory, not just metaphorically. Literally, you are moving through curved space-time, tracing a path defined by every mass you've ever encountered, every breath you've ever taken. You are a story written by gravity, and one day, gravity will write your final line. But maybe that's not a bad thing. Maybe gravity's gentle pull is not just a drag toward the end. Maybe it is the embrace that holds the universe together. Maybe it is not the thing that brings you down, but the thing that makes meaning possible. Direction, sequence, structure, a place to stand, a reason to fall. We've journeyed from birth to death, from space-time's fabric to its tremors. We've watched gravity hold galaxies and shape your breath. But now, we ask, what else might gravity allow? Because while gravity binds us, it also bends. And in its bending, there may be doorways, not just metaphors, not just dreams, but real possibilities permitted by the very equations Einstein gave us, wormholes, tunnels through space-time. Einstein's theory of general relativity allows for strange geometries beyond black holes, beyond expansion. Among them is the idea of a wormhole, a bridge connecting two distant regions of space-time. Picture space as a sheet of paper. Now, fold it and pierce a hole through both layers. A wormhole would connect those 2 points, allowing a traveler to pass instantly from one side to the other without crossing the space in between. The idea emerged from Einstein's own work alongside physicist Nathan Rosen. They imagined what's now called an Einstein-Rosen bridge, a non-traversable wormhole. But later refinements, using exotic matter, suggested that traversable wormholes might be possible. But exotic matter is the key. To hold a wormhole open, you need something with negative energy density, a kind of anti-gravity that resists collapse. We don't know if such matter exists. We've seen hints of negative energy in quantum experiments, like the Casimir effect, but scaling that up is another story. Still, the equations say, maybe. And in science, maybe is where revolutions begin. Time travel, the twisting of light cones. If wormholes can connect places, can they also connect times? In theory, yes. If you take one mouth of a wormhole and move it near a black hole or accelerate it close to the speed of light, time will pass differently for each end. When you bring the two ends back together, one will be younger than the other. Step through one mouth and emerge in the past or the future of the other. This would create a closed time-like curve, a path through space-time that loops back on itself. Time travel, the very idea conjures paradoxes, changing the past, meeting your younger self, grandfather dilemmas, and yet the math allows it. No known law of physics explicitly forbids it. But there's a catch. Quantum mechanics suggests that time travel may be self-consistent, that events rearrange themselves to avoid paradox. You may be able to travel to the past, but you cannot change it. You always did. You always were part of what happened. Time, in this view, is not a line, but a loop, and gravity might be the pen drawing that loop. The multiverse, infinite realities in infinite space. There's another possibility that gravity, far from being a fixed feature of our universe, is only one version among many. In the inflationary model of the early universe, inflation didn't just happen once. It may be happening forever, in patches, spawning bubble universes in a cosmic foam, each bubble a universe, each with its own constants, particles, dimensional laws, some with stronger gravity, some with weaker, some with none at all. In some, stars never formed. In others, black holes rule. In one, perhaps, you never existed, or perhaps you always did. This idea is known as eternal inflation. And if true, our universe is just one island in an infinite sea. Gravity is local, reality is layered, entanglement, emergence, and the holographic mind. And then there is the strangest idea of all, that gravity itself is not fundamental, that it emerges from something deeper. In recent years, some physicists have explored a provocative connection between quantum entanglement and space-time geometry. The idea, in essence, is this. Space-time might arise from patterns of entanglement. Wherever particles are entangled, sharing information instantaneously across space geometry forms. The tighter the entanglement, the more strongly curved the space. From this view, gravity is not a force or curvature per se, it is entropic. It arises from the tendency of information to increase. Gravity is the shadow of information flow, the shape of entropy, and if true, it means that space, time, and even gravity are not the foundation. They are emergent, and something more fundamental, something informational is underneath it all. A code, a pattern, a network. We are not just moving through space-time, we are moving through meaning. Consciousness and the gravity within. Speculative physics often stops at the edge of observation, but some ask, what about the observer? You are not passive. You are not a camera. You are a conscious being, aware of time, of space, of gravity's pull. You not only fall, you feel yourself falling. And some have wondered, is consciousness also tied to geometry, to information? Could there be a connection between gravity, entropy, and awareness? It is early. It is untested. But the question lingers. If gravity is tied to time, and time to memory, and memory to self, then maybe gravity is not only a force shaping stars. Maybe it is a medium through which experience unfolds, a field not just of mass, but of meaning. We do not know. We cannot know yet, but that has never stopped us from dreaming. And perhaps that's gravity's final gift. It pulls not only on matter, but on imagination. It curves, not just space-time, but possibility. So now we arrive, not at an answer, but at a horizon. We have followed gravity across the birth and death of stars. We have watched it bend time, curve space, shape galaxies, ripple through black holes, and whisper secrets to detectors buried in silence. We've seen it collide with quantum paradox, hint at wormholes and other worlds, and finally turn back toward us, toward the body, the breath, the ordinary miracle of being held. And now we pause, because after everything, after the physics, the metaphors, the math, something remains. A presence, a stillness, a weight that is more than force, a quiet gravity within. Close your eyes for a moment, take one breath, feel the pull that holds you to earth, not just physically, but existentially. It is the reason you stand, the reason you fall, the reason you can even say the word here. Without gravity, there is no location. Without gravity, there is no home. In the vastness of it, all the distances, the numbers, the cold elegance, there is something so fragile about life. You are small, a pattern of carbon and water, standing on a pebble in space. But you are not only small, because gravity touches everything equally. It doesn't care about size, or ego, or meaning. It acts on galaxies. It acts on you. It does not differentiate. And that, perhaps, is its most profound lesson. It reminds you that you are not separate. You are not a thing in the universe. You are the universe, made of it, shaped by it, held in it. Your bones are born from stars. Your breath rides the atmosphere. Your skin pushes back against the pull of Earth. And that's how you know you exist. You are always in relationship with gravity, with time, with every particle that's ever touched you, with every force you've ever resisted. And maybe this is what gravity has been trying to tell us all along. That meaning is not found in isolation. It is found in connection. Gravity does not act alone. It is the relationship between things, between mass and motion, between space and time, between you and everything you are not. You move, and the universe moves with you, not metaphorically, literally. Every choice you make adds weight to the world. Every movement is a shift in the fabric. Even your stillness exerts pull. Your body resting gently on a chair or standing quietly in the dark curved space-time. You are shaping the universe just by being. The ancient mystics said we are made of dust. Science agrees, but it adds something more. We are made of dust that remembers, and we are pulled across decades, across dreams by invisible threads we do not fully understand. We call them gravity. We call them love. We call them longing. And perhaps they are not so different. Each pulls us toward something greater than ourselves. Each demands surrender. Each shapes our path. One day, long from now, your atoms will be scattered. Your body will return to Earth. The Earth will return to the stars, and the stars will collapse into silence. But gravity will remember. It will keep the curve you once made, the weight of your presence, the echo of your motion, the quiet indentation of your being, not erased, only absorbed, folded into the larger fabric. And so this journey ends where it began, not in the equations or the telescopes or the distant nebulae, but in you, in your ability to feel the pull of something greater, to wonder, to ask, to let your curiosity fall inward like starlight toward a black hole, not to be lost, but to be transformed. You are gravity's witness, gravity's mirror, gravity's voice. You are the way the universe becomes aware of its own structure, the way matter learns to speak, the way time learns to remember, the way space learns to dream. We began with a simple question: what is gravity? But now, at the end, maybe the better question is: what has gravity taught you? Has it changed how you see the stars? How you feel your feet on the floor? Has it brought you closer to silence? To wonder? To wait? If so, then this journey was worth it. Not because you now understand every theory, but because you remembered something ancient. That being held is not a weakness. It is the beginning of awareness. It is the starting point for all motion. It is the condition for meaning,